Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about projective geometry, and particularly we considered some of the concepts in two-dimensional projective space. Today we will discuss about transformation in these projective spaces and a particular transformation which is known as projective transformation. So let us understand what is meant by a projective transformation. As I mentioned, it's a transformation, means it's a mapping from an element in a two-dimensional projective space to another two-dimensional projective space. So in this case, the two-dimensional projective space has been denoted by p square, and the other two-dimensional projective space is also p square with the same notation. The characteristics of a transformation, projective transformation, should be that it is invertible. That means there is one-to-one mapping of elements from one space to the another and the reverse. So every point in the original space has a unique point in its mapped in the transformed space. Similarly, for every point in the transformed space, there exists a unique point in the original space from where, or source space from where it has been transformed into that one. And then the other property, which is very, rather I should say, geometric, from the geometric point of view, quite informative and quite interesting, that it preserves the collinearity of every 3 points to be every 3 points. So 3 points, say x1, x2, x3, which lie on the same line, then if and only if hx1, hx2, hx3 do. So any line is also transformed into, any straight line is also transformed into a straight line in the projective space. So just figuratively, we just once again try to understand this problem, this properties of transformation. Consider a set of 3 points, and incidentally they are collinear, and I have shown with different colors. So when you consider a projective transformation, so it's a transformation in another projective space, and with colors I have shown the respective correspondences. So you can see that the mapping, and the other thing is that the uniqueness of the correspondences, corresponding pair, so which makes it invertible, and the collinearity property. So since these 3 points are lying on a line, so the other 3 points will also lying on a line, and you can also observe that because of this property, the ordering of points are also preserved. So there are some examples of projective transformation from the geometric interpretation its point of view. So you consider a projective space, say this is, as I mentioned, that in a two-dimensional projective space there is an implicit three-dimensional coordinate system which defines the projections, and in the point in a two-dimensional space is actually correspond to an element which is a straight line, which is a ray passing through the center of projection. So this particular, say, ray, it corresponds to this point. Now you consider another plane in the same 3D coordinate system, and you consider that becomes the plane of projections. So now you can see that this point and this point, they make a correspondence. So similarly, if I consider any other element in this space, and if I relate them in the same way, so say this is a point, say y, or so it would be also say y dash. So they are corresponding. So with this kind of underlying relationships, mapping, you can say that it's a projective transformation of points, because as you see that this uniqueness of the corresponding pairs are well defined here. Not only that, if I consider any straight line in this plane, it will be mapped also to a straight line in the respective image plane also. So all the points like collinear points, they are also transform points, they are also collinear. So first thing, these two are projective space. So this is also a piece, this defines a piece square, this defines a piece square, though their underlying 3D coordinate systems are the same, but they have different coordinate conventions internally on the plane. So you have coordinate axis and their origin and their conventions, they could be quite different. But still with those coordinates, in its own coordinate system, if I consider some kind of functional relationships between mapping of these coordinates to other coordinates, now that kind of transformation will be projective transformation. So this is one example, and I have just elaborated it, but very quickly I will show other kind of configurations. So I just mentioned this. So say there could be also on the same plane rotation of axis or change of scale, translation of origin in planar coordinate system, use of affine coordinate system in plane. So consider a coordinate convention where these two coordinate axes, they are not rectilinear, they are not perpendicular. But whenever you measure, whenever you express any coordinate value, now these distances, they are parallel to the corresponding, these distances are defined by the parallel rays, length of the parallel lines, which are parallel lines of those, forming those parallelograms. So this is an affine coordinate system. So even with these coordinate values and in any other coordinate conventions, there also you can find, you have the transformation which is a projective transformation. A few more examples. So this is just with respect to one plane, within the plane or from one plane to another plane under the same implicit projective three-dimensional system. But you can consider different kinds of notation configuration. Say in this case, what you are considering, you are rotating the image plane around the axis. Here also your underlying world coordinate system remains the same, but the mapping of points through the same ray of projections passing through the center of projections, that correspondences can form a transformation, can define a transformation, can define a mapping, and which is a projective transformation, because lines are also transformed into line. It is invertible, and these are two projective spaces. This is another example where you have two, in the three-dimensional aspect, there are two planes of projections. There also you can have the same thing. Now this is a bit different configuration. Now this one I am talking about. You can see here the three-dimensional, the coordinate system, the scene coordinate system is actually two-dimensional, not three-dimensional. But they are forming images again into two views, and this is one projective space defining its center of projection and image plane. This is another projective space defining its center of projection and image plane. Now these are the image points of the same point on a two-dimensional plane. So this also forms a projective transformation, because if there is any line in this space, so all the points will be, so all these these points, so this line will be also projected as a line, this line will be also projected as a line. So the transformation between these two spaces, they are also projective transformation, because lines get transformed into also lines. So that is the third conditions, and they are invertible. There are transformations between two projective spaces. So from the multi-view imaging consideration also, from that point of view also you can see existence of a projective transformation. Of course, the constraint here is that your scene is a planar scene. That means on the scene points they lie on a plane. Now, one of the interesting fact of this projective transformation, which could be proved theoretically, you can derive it theoretically, and we will show some intuitive reasoning for that also, that only one form is possible. It's a function, as I mentioned, it's a function. So, which means that if I consider in general in a projective space some elements, say x1, x2, x3, say this is one element in the 2D projective space, as I mentioned that this is an element in 2D projective space, and in the homogeneous coordinate system this determines the scale, we know that. And suppose you have another element, projective element in another space. So these are two different projective space I am talking about, and then you are having a transformation, which means I may write x1 prime equal to some function of say x1, x2, x3, x2 prime equal to some function of x1, x2, x3, and say x3 prime is some function of x1, x2, x3. So I can consider this kind of relationship where a functional form is not yet specified. We say that these are the functions. So that is what is transformation. Now, what is interesting that these functional forms, there is only one form, one kind of algebraic expression, and that is basically it's linear, and also it is invertible, because as I mentioned, invertible property comes from the property of the projective definition of projective transformation. So it has to be invertible. So linear means I can express it in terms of any matrix operation. That means all these functions, they are in the form of a linear function. So I can write it, for example, x1 prime is equal to say, let me write say h11 x1 plus h12 x2 plus h13 x3. That is what is the linear function in terms of its coordinates of the projective space. Similarly, x2 prime, similarly I can write h21 x2 plus h22 x2 plus h23 x3, and x3 per prime as h31, this one h21 x1, h31 x1 plus h32 x2 plus h33 x3. So this is the linear expressions. So this can be conveniently represented once again, since we are using this kind of column vector form for representing points. So this can be conveniently expressed in the form of a matrix multiplication. As you can see that these are the elements of a 3 cross 3 matrix. We represent it as a matrix H, which is 3 cross 3 matrix, and which is invertible, which should be invertible. Then only it is projective transformation. Now this is the only form. So any projective, when there exists any projective transformation, that means there exists this kind of there exists some 3 cross 3 matrix, an invertible matrix or non-singular matrix, which expresses this kind of relationships. So you think about that transformation, some of those cases, say I mentioned that this multi-view geometry cases, that you have a planar scene and you have two projective system. Let us consider two cameras which is viewing these points from this scene, and this is the center of projections, and say this is the points, say this is point, say let us say this is x, and say this is y, say this is point x, say this is point y. And similarly, this is another camera where you have these projections, and say this is x prime and y prime. So x is mapped to x prime, y is mapped to y prime. Note that these are all points. This is not coordinate. I'm talking about points. So x has three, in the projective coordinate system, two-dimensional, it has a three coordinates. Y also has a three coordinates, and this kind of relationships exist. Then there exists some transformation H from this space to this space in this form, so that the coordinates of x would be transformed into x prime. Similarly, coordinates of y prime, and any other points if you consider. Suppose this is a point Q. So if I again use that same kind of rule, say this is a projection of Q in this space, and similarly this is a projection of Q prime. So if I write x prime, there exists H such that I can write x prime is Hx. You note that these are all three vector represented in column form by their coordinates. Similarly, y prime can be written as Hx primes. If such H exists, similarly Q prime should be also HQ, and all these kind of points, whenever you find this kind of mapping, there exists some H. Now, of course, that H needs to be determined, or we can only say there exists H because of this particular property, which is a very, I should say, a very strong property, and which gives you a lot of information about the functional form of these kind of relationships. So this is the advantage that you have when you consider any projective space. So that's what, this is a summary. As I mentioned, that the coordinates of these points in the original space and in the transformed space, they are related by such transformation, by this kind of matrix relationships, matrix multiplication relationships, which expresses that linear relationships. And I can write it in this form. And please note here, since this is a projective space, so if I consider this, and if I multiply all the element by k, so I get the mapped point as k as a scalar multiplication of these coordinates, but which is equivalent to, in the projective geometry, as you know, that the scale can be, they are equivalent up to scale. So they are equivalent. So whether it is h or whether it is kh, it denotes the same transformation, and the points are equivalent. These points are same. So that is another aspect of this projective transformation. It's an element of the projective space. And because of that, it has 8 degree of freedom, because one of the element you can consider that is acting like a scale, and you can express all other values in proportion to this value. So that's why now you have 8. So you can fix this one, and then there will be 8 such unknowns. So there are 8 degrees of freedom in this case. So one of the technical term of this kind of projective transformation matrix is called, projective transformation itself, one of the technical terms is that it is called homography. Homography is a very common term used in this respect, and which means exactly the same thing, that is projective transformation. And the entity, this H or this transformation matrix, is called homography matrix. So I will just show you that how this kind of linear transformation of two linear transformation can preserve the collinearity. So you consider L to be a line in the projective space, and suppose a point x on L gets satisfied, okay, which means, if it's satisfied means x and L are orthogonal. If you use point containment relationship, x transpose L should be equal to 0, or L transpose x should be equal to 0. So we can write in this form, and now let us see that what happens for that point in a transformed space. Whichever point which is satisfying these relationships in the original space, so what happens to them in the transformed space? Now I can write this particular expression in this form. Say L transpose H inverse Hx, because H inverse and H, it makes identity, and then algebraically it is these two are equivalent. Okay. So now you can see this Hx, this becomes the transform. This is the transform point. So any transformation, any point which is lying on this line, all the transform point which are lying on this line, I mean satisfying this equation, they are also lying on a line. Now this could be also another line, because what is L? L is a line, and we know that L is also an element of projective space, which is a 3 cross 1 column vector. Now if I consider this particular computation, check the dimensionality. L transpose is 1 cross 3 because it's a row vector, and H inverse, it is 3 cross 3. So it gives you a 1 cross 3, right? So which means I can write it H minus TL transpose. So this becomes like L transpose, L is the line, similarly this becomes your line, which is a 3 cross 1 column vector. So I can write in this form, and then this is the transform line of L, because this transformation shows that containment of Hx in this line H minus TL. H minus T is the transpose of inverse of H, which is also 3 cross 3, and L is 3 cross 1. See, in this case the total composition will be 3 cross 1, which is a line. So H inverse, transpose of H inverse into L is the transformed line of L. Now, of course, it shows that if I apply any linear transformation on a projective space, the lines are also transformed into line. Or points which are collinear, it will remain collinear. So in that way, linear transformation is a projective transformation. But it is harder to say that any transformation which is projective is also in the form of linear, which I am not discussing here at this stage. So what are the implications of this? That as I mentioned, if there is a homography, there exists a unique H which is a 3 cross 3 invertible matrix. Now this uniqueness should be again taken in the as a pinch of salt, because you know that H and KH, they are equivalent. So it is unique up to scale. It is unique up to scale, and it is a 3 cross 3 invertible matrix. Since the functional form is known, it is easier to estimate. That means if I give you the corresponding input data, say some of the point correspondences, from there we can estimate this H. Because we know the functional form, we can write those equations, and then we can perform, we can solve the equations, or we can perform some kind of least square error methods or optimization methods to get a good estimate corroborating with that set of points, set of point correspondences. I mentioned already H and KH are equivalent, and K is a scalar constant. So in this case, number of unknowns in H is 8. And so in that case, as I say, that if I consider a problem, that I will give you a set of point correspondences. So you remember this configuration once again. Suppose you have a planar scene, and you have two images of the same scene. So there are projection. This is one projective system, one projective space. Say this point X. Similarly, say this is the center of projection. This is Y. Say this is another point, say Y, and say this is this. So let me write it as X. This is say Y. Say this is X prime. This is Y prime. Now, if I know the point correspondences X and X prime, similarly point correspondence of y and y prime, right? So, and let us not bother about the scene, because usually what will be in our hand, we can observe only these two images. We do not know about the three-dimensional arrangement of the planar scene. So we observe only these two image points, and they are in the image coordinates. If I know these points, and if I somehow can get the point correspondences either by visually or by some computations. Now the question is that from these point correspondences, can you get H? So that you can say that x prime should be equal to hx, y prime should be equal to hy. So if you have a number of point correspondences, now you can see that each one of them is giving you some set of equations. Now since the projective transformation, as I said, that it is up to the scale. So it is x prime equals hx. It is, I should say that it is it is not hard it may not be hard equality. It could be a kind of equivalence, or there exists some k which is considering this. So what we can do, we can express rather these equations. So it seems there are three equations, but to disambiguate these scale relationships, what we can do, we can express in the form of non-homogeneous coordinate systems relationships. That means we will be relating with the non-homogeneous coordinates, or where the scales would be taken care of. And then we can set equations. So we can show that from each point correspondence you can get two equations. We can show that, and I will be discussing that. So since there are two equations from each point correspondence, and since there are 8 degree of freedom of h, that means one of the element you take it as a scale and set to some value, and then you can express these relationships, and then you have to determine only 8 coefficients with respect to that element. So you have to have 8 unknowns, 8 equations for 8 unknowns. So which means 4 point correspondences can give you the required set of equations to provide H. So minimum 4 point correspondences are required to estimate H. So that is the kind of conclusions from this observation. Since there are 8 unknowns, so as I mentioned, x prime equals hx, it provides you 2 independent equations. So these are the equations. If you can see that what I did, that I considered instead of hard equality of homogeneous coordinates, I considered hard equality of the non-homogeneous coordinates, which means that x prime is x1 prime, x3 prime, and we considered the this point, x is in the canonical form, it is in xy1. So because your observed image point, we consider that is in the canonical form, it is in xy1, and one of them in the source, and the other one you are expressing their respective coordinates in the non-homogeneous coordinate convention. So you are dividing by the respective scale. So if I show you that what you are getting, x1 prime, x2 prime, x3 prime, and these are the element h11, h12, h13, h21, h22, h23, h31, h32, h33, and you multiply with the point in the original space, which I am expressing in terms of xy1, because this is the observation. You have already observed this point, and this being mapped here, but what you have observed x prime, which is again in the canonical configuration. That means my observed point is x prime, y prime 1, though I cannot simply equate these equal to, I cannot equate this equation with this, because there could be scale relationship. So what I can do, I can consider x prime equal to x1 prime divided by its scale x3 prime. That's what we did. Similarly, y prime equal to x2 prime divided by x3. That's what we did. So you get two equations here. And this could be converted into two linear form, because what are the unknowns? Unknowns are these parameters. These are the unknowns. So I can rearrange this equation. I can see that those are also forming a linear equations. So if we have 8 such equations, and one of them you can, as I mentioned, that you can set one of the parameters, say h33 equal to 1. With respect to that, you express other. So once you set h33, the scale is 1, then all other elements are unique with reference to this. Only problem is that in some configuration, this element could be 0, then you cannot take is equal to 1. So there are some cases where this kind of setting will fail and it will cause problem, but in most cases you will find that on the average it will work in most cases. So anyway, let us consider first, for the sake of simplicity, that h33, which we always take as 1, some value, non-zero value, and it is not 0 in this particular case. So let us assume that. So now if I write those equations, so as I mentioned, minimum 4-point corresponding needed, and I'll be explaining that part. First, let us we consider this. Say suppose the same image I discussed earlier also. When I have discussed with respect to the vanishing point and vanishing line, where you can see that parallel lines, they appear to be converging. So when we say removing projective distortion, it means that what I would like to do, that the parallel lines which appears to be converging, can we map them? Can we define a mapping on them so that again they become parallel? So this kind of thing. So I would like to make this image, again I would like to make another projective transformation so that these two lines, they can be considered as parallel. And also not only that, I would like to have a front facing, it looks an oblique plane. I would like to have a front facing plane. So I can define some mapping in my own way. So what I can do, that I can select 4 points in a plane with known coordinates. So these are the points I have selected, say 4 points. So these are the corner points I have selected. And then I have assumed some coordinate convention, which is with the fronto-parallel orientation coordinate convention in my. So I would like to make this image fit this image into this frame. So within this, I define one coordinate system and establishes the correspondences. Say this point corresponds to this, this point corresponds to this, this point corresponds to this, and this point corresponds to this. So with these correspondences, I can compute H and then apply it. Then I will get this kind of distortion corrected. So let us see. So we can form such equations. So typically from single point correspondences, you get 2 such equations, because I know this coordinate system, I know this coordinate in my own defined coordinate system. On my own I have defined. I am free to define some coordinates which is logical, and so we may preserve certain kind, we can consider certain kind of aspect ratio of this rectangle. And this coordinate is given by the image itself. So from there I can observe this and I have my own defined coordinate system. And these are the 2 equations. As you can see that these equations are linear in terms of these coefficients, which are unknown here. So I can express these equations in the form of linear, and by setting h33 at 1, we can solve this one. So if I solve and if I use that transformation to map all the points, you can see that this particular board, notice board, which was looked like bit obliquely faced, now it has become fronto-parallel, and sometimes it is easier to interpret with this from this position. As I mentioned that it may not work if h33 happens to be 0. So just to once again elaborate this part. So this is the equation you have to form, and in fact these are the coordinates incidentally which we considered in this particular task. So in my defined, that box was 500 by 900 box, right? And I considered the coordinate 900, 500, 500, 900. So you can see that this is the size. So if I use those equations, if I write those equations from each point correspondences, I get 8 equations, and also I set H33 equal to 1. Then I get all these equations, and once I solve them, so this is the matrix form. I am writing these equations in the matrix form. So you know that by simple matrix inversion you can do it, because what is the size of the matrix? You can see that this is 8 cross 1, but this is 8 cross 8, and this is also 8 cross 1. So finally you get you can compute inverse of the matrix, solve by matrix inversion, and it happens to be your transformation matrix for doing that kind of corrections or straightening out of those oblique lines in the fronto parallel plane. So you can see that some of the elements looks very small, but actually they have their effect in the case of transformation. So I am just showing it in a bit more zoomed form. You can see here that there are writings, but when I do it, you can also see that this writing is better readable. So for example, I can read here, so this is one of the finest and magnificent Mahayana monasteries, known for its display of the greatest number of jatakas. Whereas if I want to read these things, you can read it, but with much more difficulty. So these are certain applications of this kind of homographic or projective transformation. Now these computations, let me explain it, elaborate it a bit more. Actually, the method what we have applied, that is only for 4 points I have shown, matrix inversion. But what happens that as you have understood that there could be a lot of many noises in your observations. There could be computational errors of building point correspondences, and that may make some problem. Even the numerical stability sometimes may not be there because of large numbers. So to address those issues, what we do, we instead of only these 4 point correspondences, what we do that to make it robust, we take a more number of point correspondences, so that so that we can either select some good point correspondences, or on the average we can make the result robust. It is not dependent on a noise on a single sample. If there are number of sample is very small, then a particular noisy sample will cause a lot of error. So when you have a large number of samples, then that get averaged out. So there are different reasons for that. So instead of 4 points, we take more number of points, more than 4, and it could be as many as say 7, 8 or more than that. So, and from there you get a number of equations which is this number is larger than the requirement of the minimum. So it's an overdetermined set of equations. So there you apply the least square error solutions. And these equations, what we can do that to make this equation projective, or to take into consideration of the scale, instead of considering hard equality, as you know that H and KH both are solutions, what we consider that these are 2 vectors, because these are column vectors, and since equality means those 2 vectors should be parallel. So that is the meaning of equality. So because of 3 vectors, we can take this particular liberty of doing these operations, because if they are parallel, then what we can do, we can take the cross product of these 2 vectors, and each cross product will give me 3 components, and since they are parallel, all of them will be equal to 0. So we get actually 3 equations, but what we can show that out of those 3, 1 is dependent upon the 2. So there are actually 2 independent equations. So once again you get 2 independent equations from the same observations, and where you are also taking care of the scale ambiguity. So let us consider this is xi prime is xi prime, yi prime, wi prime, and you consider your once again your point xi is xi yi 1 in the canonical form. So we can write these equations in this form. So you can see that this is the cross product of three vectors, and that would give you this equation. So just to once again explain the convention, you can see that homography matrix or projective transformations, here we have instead of columns we have expressed them instead of the row. This is a submatrix representation. So each one is 1 cross 3 of dimension because of the transpose operations. So we are considering them as a row. We are taking the row of the homography matrix. So if I perform hx multiplication, say hxi, so what I am doing, h1 transpose xi, because in the matrix multiplication first row and then the column, that would give me the first element. So h1 transpose xi. So the dot product of row vector and column vector. Similarly, dot product of second row vector and column vector, and dot product of third row vector and column vector. That would give me the equivalent transform point, which is also represented as a vector. And now if I perform the cross product, so xi prime is written as say xi prime, yi prime and wi prime. Note that this notation is overused. This x font is very different and this one. So that is what, that is how we are distinguishing them. And this one is given this in this form. So in the matrix notation, I can write say I, j, k, since xi prime comes here. So xi prime, yi prime, wi prime, and this is h1 transpose xi, h2 transpose xi, h3 transpose xi. Now you see that from the ith component, it is yi prime multiplied by h3 transpose xi minus wi prime multiplied by h2 transpose xi. So this gives you the first component. Similarly, you get the component for j and component for k. You perform these operations, then you will find that the cross product will give you these three components, and which should be equated with 0 column vector. Now this 0 is not a simple 0. This 0 is actually, it's a 0 column vector. So you get three equations. This equal to 0, this equal to 0, and this equal to 0. So these three equations, but there are two independent equations, because if I multiply this equation with xi prime and this equation with yi prime, we can see that this component and this component, they get cancelled, and what you get effectively, the third one. So you get the third equations from the first two equations. So that's why now you get two independent equations out of this operation. So it becomes redundant, and so each point correspondence will give you two independent equations. So what I can write in this case, that once again I have written it in a clean way, that how these equations. So these equations are reformatted, where since your unknowns are the elements of your matrix H, that is the homography matrix. So I have expressed those elements. These are all column vector. H1 is a column vector, but this H1 is a row of the H which is represented in the form of a column. Similarly, H2, because you know that H1 transpose is actually representing the row, but the row itself is represented as a column. So all the 9 elements of H, they are now concatenated, row wise concatenated. So first row, this is the first row, this is the second row, this is the third row in the column form. So all the 9 elements are concatenated, and they form a column vector of size 9 cross 1. And these are the 3 equations and then give 0. But I will just take out this equation because this is redundant. So finally, what I will get only AIH, where AI is the first row and second row. Form a matrix. Now each element, this is actually a row vector of 3 cross 1. This is not simple 0. You can check with those equation formations. So this itself is 2 cross 9, because this is 3 cross 1, this is 3 cross 1, this is 3 cross 1. You can remember Wi prime is scalar and xi transpose is the transpose of the column vector of xi. So this xi is actually, these are vectors. So this one, okay. So some notational ambiguity is there. You consider this representation. The italic notations, these are italics are meant for scalar values. Here, the notations. So this should be taken as the vectors. So each row is of size dimension 9. So it is 2 cross 9. Each row is 9, means there are 9 columns. And this equation, this H is 9 cross 1. So you have the dimension of AI is 2 cross 9. So one single point will give me 2 equations, and if I solve the H by setting H33 equal to 1, I can take out that last term, all the term related to the H33, I can, instead of equal to 0, I can make it equal to non-zero elements, and which is a non-homogeneous equations. Because if you have non-homogeneous equations, then you can apply the least square error method by solving it. So I have already discussed this part earlier also in several lectures, that when you have this kind of least square error method for non-homogeneous equations, you can simply use the pseudo inverse technique. So this is a single equations, and I can consider stack of these equations for each point correspondences. So if there are n point correspondences, then the dimension of A would be 2n cross 8. So this AI, this is actually 2 cross 8, because H tilde is represented in this way from H. This is a vector which is 8 cross 1, and then this is the H33 term which is set to 1. So this equation, as you know, that your objective is to minimize this norm of this, actually square of the norm you can consider, and then the solution would be, so this is a solution, A transpose A inverse A transpose. This is the pseudo inverse. Once again, let me show you the trick by which you can remember. Suppose I set this equation. So this is the equation at this stage. You know that A is of 2n cross 8, B is this, again stack of these values, and that would be also 2n cross 1, and H tilde is, it's basically H tilde is 8 cross 1. So H tilde equal to B, and then you multiply both sides by A transpose. Now you take the inverse here. So H transpose is A transpose A inverse A transpose B. So that is the solution. So this is the direct linear transform method for solving set of non-homogeneous equations. Once again, the problem is that if there are if H33 is 0, then this technique does not work. So in general, what we try to do, we try to solve the homogeneous equation directly, instead of setting a value H33 equal to 1 and then converting into a set of non-homogeneous equations. Why don't you solve with directly the homogeneous equations? So in that case, as you understand that this matrix A, it contains always a stack of all these 2 cross 9 submatrices. So each one is of 2 cross 9, like the previous one, because H is of 9 cross 1. So if I consider the dimension of this matrix, it is 2n cross 9. So I can rewrite these equations in this form. But now, since it is homogeneous, AH equals 0, so we have to minimize this. We have to minimize a norm of AH such that your H is unit vector, because you can make it scale also. So this should be the thing. H and KH should be a solution here. So once again, you just put a restriction to minimize that H is a unit vector in this case in the solution. Now the minimization in this case, it can be shown that if I consider the eigenvector of the solution would be the unit eigenvector of smallest eigenvalue of A transpose A, because you are trying this norm. If I consider this norm, minimize this, basically I will be minimizing this square. So what I can write here, so this could be written as AH transpose AH. Equivalently, this could be written as this, which is given as H transpose A transpose AH. So you can show that the solution of this H is equal to the smallest eigenvalue, because that would give you the smallest smallest eigenvalue would be the smallest value of this square of the norm, and the eigenvector corresponding to the smallest value would be the solution. So this is how you solve for H in the case of homogeneous equations. That would give you also the respective homography matrix, and as you know that this is still up to the scale. So in that case, if you also get a matrix H, you can simply multiply by K also to get equivalent matrix H. So they are of the same solution. Now this is one kind of error criteria that we discussed, but there could be other error criteria. So there could be other way you could try to solve this problem, and which may not be following this kind of algebraic criteria. So this is the algebraic method of solving the problem. So these errors are called algebraic errors, but that is the least square error method what I mentioned. But you can consider from the point of view of geometry also. So geometrically what you consider, for example, I have two spaces, say the source and the destination or transform space. So I am given the point correspondences. So this point corresponds to this point. I need to find out H. Similarly, say this point corresponds to this point. So I have to get such an H by applying which, say I get a point here. So the distance between these two, that shows how good is my estimate. I would like to get them as close as possible to my observation. Now it may be noisy also. So one of the things what I can do, that for all the points, it should be such H which will minimize the sum of square of these distances. And again, since we know that if this is H, its inverse also should be working. So if I take the original point, observed point in the transform space, let me apply H inverse. It will also give me some point which would be close to my point of observed point in the original space. So these distances also should be minimized. So we call it reprojection. So this is called projection error, this is called reprojection error. I can go with only projection error, or I can go with both projection and reprojection error. So this is a geometric error, which is a projection error, that sum of square of all these projection error, that defines the corresponding optimization criteria. So Euclidean distance we are considering, or geometric error with reprojection. As you can see, I have considered both the deviations from the mapped point to the observed point, or the inversely mapped point to the observed point, and that is. So there are different. So this make this kind of optimization problem is a nonlinear optimization problem, and there are various nonlinear iterative optimization technique such as Newton iteration or Levenberg-Marquardt method. Those techniques can be used to solve this problem. So one of the some of the tricks one can also consider to handle large numbers, etc., that we want to make this kind of estimation problem is more robust because it associates with large numbers. So can I normalize this this kind of mapping? So can I normalize the input data so that your estimation of transformation matrix remains within the numerical limit, within the numerical limit of computations, numerical representations, within good numerical representations of your elements of H. So you let us try to understand that if I apply transformation, suppose if I apply transformation T on Xi and say T prime on Xi prime, then what happens to the structure of H? Can I recover H from this? Suppose instead of computing estimating the H from Xi and Xi prime, if I estimate from Yi and Yi prime, can I get H by knowing these two transformations? We can show that it is possible because if I estimate from Yi, Y minus 1, so this is the relationships. You can see that X prime equals Hx, and then replace X prime and X by these respective transformations operations, which is invertible transformation by the way. So there you can see that even the transformed points, they are also related with a transformations, 3x3 transformation, which is non-singular transformation matrix. So instead of H, we are estimating this matrix G, and by knowing T prime and T inverse, from G we can get H. But one of the problem here is that because you are applying optimization technique and handling least square error methods with certain constant optimization, so the result what you get because of this, that result may not be the same if I apply it, if I perform the same operations on the directly observed set of points, but they should be very close. So it's a possible solution, but it is not the exact solution of the problem given that from that input data, but it is one of the good solution that we can do. So this trick is used for the numerical stability point consideration. So that's what it is not equivalent. So that's why you consider one such transformation which makes it more robust, and in this case we transform the point set so that its center becomes origin and the plane and average distance from it is √2. So this is the transformations usually we do. You see that all the x coordinates and y coordinates in the set from the input data set in each space, they are basically normalized as we do for the case of normal distribution, subtracting mean and dividing by the scale factor. So you get the respective transformations, and then you can apply this DLT on transform point and recover homography from the homography of the transform point sets. So with this, let me conclude today. Stop here, and we will continue this discussion in the lecture. Thank you very much for your patience and listening.